Welcome to part 2 of week 1 lecture. We'll be following chapter 1 of our textbook by David Kong. So the key points of the chapters are this. The objectives, the aims of software engineering is to improve programmers' productivity. So that we can lower the software development costs and also lower the time to bring a product to the market. Because lots of time, many people will see the same needs in the market. And if we're too slow in bringing a product to the market, then our competitor will do that before us, and they may have a slightly better chance than us, as long as they also deliver a quality product. Okay, and if we can build good quality software, and our users will like it, and it's more desirable. And we can see software engineering as three kinds of interrelated activities. One is the software development process. So how people work together to create software. Quality assurance. How do we ensure that we're producing good software? And about how to manage different activities. In the last 20-30 years, OO has become the trend. And so now, in the old days, we think of a computer system as many functions or features, and then we decompose big features into small features. So that was the old way of developing software. But very soon, people find that looking at a system as a collection of objects, and objects sending messages to each other, interacting, results in more maintainable software. Okay? And inheritance in class libraries also help us reuse objects that someone else has created for us, like classes. And if the classes other people created do not fit our purpose 100%, we can extend the existing classes to create new classes, child classes, and then we would use our own extended child classes. Why software engineering? First of all, software is very important these days. It appears in any product. There used to be mechanical products, now have software components in it. Most of you may be too young to know that in the old days, we have something called video cassette. And if we want to watch a movie, we go to the video store, rent a cassette, and then we take it to a player we have at home, and then press the play button. But we press physical button, and almost if there are 5 buttons on the machine, that means the machine probably has 5 features, 5 functions. But now the machines are all software driven, menu driven. So each level of menu, it can take us to another level of menu. So we can, even in a small phone, we can have hundreds of functions to use. Okay, even though it has 10, 15 buttons only. So things are very software driven now. even your washer machine at home that you use to wash laundries, or even a car, uh, not to mention the auto navigation, that a car that can drive itself without a driver. Even a very basic car use computer software to control how to mix the right amount of air for combustion with the fuel, and based on how much the driver press on uh, the gas pedal, like how much. So those we were talking about here, we can call them embedded system because they are part of a mechanical device or an electrical device. So the embedded system are some additional software to make it very powerful, very useful, very versatile, that can do all sorts of different functions. So that is embed that are embedded systems. And software engineering, uh, as we mentioned, help us to manage very large software. Uh, it's not uncommon for software system to contain millions of lines of code. In fact, I have worked on an insurance system when I was in Canada that has many million lines of code. And at this point, software costs are 90 to 95% of total system costs, comparing to just 5 to 10% of the total cost 2, 3 decades ago. That means every dollar people spend on a computer system, uh, 90 cents goes to software, maybe just 10 cents go to the hardware. But in the old day, it's the reverse. Okay. In fact, I worked with IBM before, but I was told by the more experienced people that IBM used to sell the hardware, and the hardware was their main income. And they either give away some software or they sold the software at a very low price, okay, at a very small fraction of the hardware. But of course, I'm talking about 30, 40 years ago. So IBM at that time, okay, those people at IBM was not smart enough to know that software become the king uh, of the future. So they hire a young fellow, Bill Gates, okay, uh, with his partner to develop the disk operating system for their IBM PC. Okay, and of course, with just two person, and of course later, Bill Gates did a good job, and then that DOS later on evolved to Windows, and he made lots of money. Okay, so but Bill Gates' original company was much smaller than a small team in IBM, but IBM did not know about the future of the software at that time. So they gave away the opportunity to Bill Gates to build a big empire that eventually worth more than the whole company of IBM, even though Microsoft was once smaller than a small team in IBM. Okay, that's very interesting history. So, and by software engineering means we employ some systematic, perhaps repeatable method to write software. So we want to be able to repeat the productivity, repeat the quality when we do things through systematic approach. Um, yes, we know we need teamwork. The figure here shows a software engineering produces an average of 50 to 100 lines of source code per day. You may think, oh, how come? As a student, I can probably write this number of lines in 1 hour. How come a software engineer requires one day to do that many lines of code. Um, but don't forget that there are lots of quality assurance and there's also coordination between team members that will slow us down a little bit. I mean, actually, not necessarily a little bit, but sometimes significantly. So that's why a, a software engineer cannot write 100 lines of code in an hour. Okay. So we need, in real projects, many people needs to work together to develop. They each work on a small piece. The hard part is to integrate all the different pieces written by different people together at a later time. Okay, so that is very challenging, and and also that is part of software engineering. So there are three main challenges. Uh, you need to come up with the identify the problems, and you designed a very conceptual solution. Okay, you have not written any code yet, but you have in your mind what kind of product would solve the problem. And then different teammates will need to communicate effectively. We'll be learning a modeling language called UML to help team members to communicate with each other. And in a project, people, different people need to coordinate their work so that they would not wait for too long because they are waiting for someone else to do their work before they can start. So we try to make people work efficiently. Okay. Um, so one kind of main activities in in software engineering is we call them life cycle activities. Uh, there are three kinds: the software development process, quality assurance, and project management. It affects the programmer's productivity, software quality, and the cost and the time. The author abbreviated these four elements as PQCT. Okay, when you see PQCT in the textbook, you know the author is referring to productivity, programmer's productivity, software quality, the project cost, and time to market. Let's talk about the first big thing, software development process. It tried to turn initial concepts. Someone just may have a vague idea, an idea of a product, okay, but the product never exists. So it turns into something operational, an actual product to run in the target environment. So the analyst or the project manager would identify, or the customers would identify some business needs, and then they conduct a feasibility study. Feasibility study try to see whether the project is feasible. Is it possible that we can do that? Is it technically or technologically viable? Like, can we do that with existing technology, or do we have enough resources, money uh, to do that development? So that is the work in feasibility study. So it so the people write down the requirements that the system needs to deliver, and then the team members will design, will implement, will test, and deploy the system to the target. So these are the design, implement, test, deploys are the kind of activity that people would do. And this is one of the well-known uh, process. It's called waterfall process. Uh, we call it waterfall because things generally like water, uh, it goes from top to like flow downward. So after someone has has done some system engineering, like look at the whole system, how things would fit together, then they identify the software requirements, and then they design very high level what components, big components, are necessary, and then they go inside each component to code it, and then they test each component. And with integration, they fit the different components together to make sure that once they are fit together, they still work. And then we take the product to the user, or with the help of user, the tester would see if the product we have integrated together from the components are acceptable. And then the software go into maintenance mode. Sometimes we will add small features, sometimes we would go to fix some software bugs. So the waterfall means it's like it flows from the mountain to the river. The water goes down. Occasionally, if we see a problem, we go back to the previous step to fix the problem. So that's part 2 of week 1.